Swayam Prabha. Digital India. Educated India.
Namaskar. So, in today's session we will discuss the modeling of electrical systems. Basically, this particular aspect you have already understood because we have discussed throughout our course. So, we will recap that what is the modeling of electrical system, and then we will compare the electrical system with the mechanical system, and we will try to identify what are the analogies in the mechanical system with respect to the electrical system. So, let us start the discussion of today's lecture. So, as we have already seen that modeling of passive electrical elements, we have discussed resistors, inductors and capacitors. So, resistors are, you can say that the voltage drop across R is ER, which is given by R into I at any time t. Similarly, for the inductor voltage drop across L, that is EL, can be given by L di by dt. And for the capacitor, we have seen the current I basically in terms of the voltage across capacitor. So, that is I is nothing but C d the voltage across the capacitor at any time t. So, C d by dt is the current which is flowing through the capacitor. So, this is what we have already discussed. Now, let us see what are the governing equations and the laws we have discussed till now. So, for resistors we discussed that the Ohm's law basically defines the voltage drop across the resistor, and it says that the voltage drop, that is ER, across a resistor is proportional to the current I flowing through the resistor. And as we just discussed, the drop across resistance is given by current I into resistance value R. In case of inductors, we just now discussed that the voltage drop, that is EL, across the inductor L is proportional to time rate of change of current flowing through the inductor. So, we say EL at any time t is nothing but L di by dt. For capacitor, we discussed in terms of current, we saw that the I is nothing but C dEc by dt. So, if you take the voltage, if you want to represent the voltage in terms of current and capacitance, what you can write, the voltage drop, that is ECT, that is EC at any time t across a capacitor C is proportional to the integral of current going through the capacitor with respect to time. So, we write EC is nothing but the integral of 1 upon C I dt. Now, for modeling of electrical networks, we used the classical way of writing the equation of electrical network, and it was based on the two methods. One was loop method and second was nodal approach, and these two approach are formulated from the Kirchhoff's law. So, what we discussed that the nodal method, that is basically based on the Kirchhoff current law, and it says that the algebraic sum of all currents entering a particular node is 0. For Kirchhoff voltage law, we also said that it is loop method, in which the algebraic sum of all voltage drops around a complete closed loop is 0. So, these were the two major laws which we used in finding out the governing equations for the electrical circuits. Now, let us take one example and we will see how the knowledge which we have just gathered related to the electrical circuit, how we can transform it into the model of the electrical circuit. So, let us consider the RLC circuit which is given in the figure. Now, when you use the voltage law, so ET is the applied voltage, we have resistance R in series with inductance L and the capacitance. The voltage across capacitance is EC and current flowing through the circuit is IT. So, what we can write? The applied voltage E is nothing but the voltage drop across resistance, inductance and capacitance. So, we write that is equal to ER plus EL plus EC. Now, the value of applied voltage E you can write as EC, that is the voltage across capacitance, plus L di by dt plus R I. Now, we also know that the current which is flowing through the circuit is nothing but I equal to C dC by dt. So, if you take the derivative of this equation with respect to time, what we can write? We can write L d2I by dt2 plus R di by dt plus dEc by dt. So, dEc by dt you can simply replace with I by C. So, you get I by C equal to d by dt. So, this is the equation which you get when you combine both of the equations. Now, the equations which we have got, this main equation which we got from the Kirchhoff voltage law, and then this is the value of current which is flowing through the capacitor. So, we will use these two equations to model the electrical circuit using signal flow graph and the block diagram. So, let us see how we draw the signal flow graph of the series RLC circuit we just saw. So, we have two equations. So, first is that is E is equal to EC plus L di by dt plus RI. So, let us take di by dt out. So, we will take this as this on the left, then we rearrange the equation. So, what we can write? We can write di by dt is nothing but 1 upon L E minus 1 by L EC minus R by L I. So, this is the first equation we get, and second we already have, that is C d C by dt is equal to I. Now, we have got these two equations. First we have to specify the nodes. So, as we know that generally we consider the voltage across capacitor and current flowing through inductor as the two important state variable, or the differential equations. If you write, then you write in terms of EC and I. So, we take these two as a node. So, the output which is required from the particular circuit is EC. So, EC we consider as an output also, and then the other variable which we have is current I. So, we have got these two nodes. Then third one is the input, input is ET. So, we apply we add the node ET also. Now, to show this particular equation, what we need? We need di by dt. So, we add another node, that is called I dot, because di by dt you can also write as I dot, and dEc by dt also you can write that EC dot equal to I. So, you specify I dot and also you specify EC dot. So, now you have got all the nodes which are required to represent the signal flow graph. Now, from this equation you can see that I dot is nothing but equal to 1 by L into ET minus 1 by L ECT minus R by L IT. So, now we will connect the join and we use the gain formula here. So, what we get? We get I dot is nothing but 1 by L E t. So, we use the gain of 1 by L to connect E t to I dot. Then we have E c with gain minus 1 by L. So, we connect the value of E c t with the gain equal to minus 1 by L. Now, this we have got. Third is I. So, I is connected to d I by dt with minus r by L as a gain. So, you connect I with I dot with the gain equal to minus r by L. So, what you have got now? You have got the equation connected to this particular node. Now, since you know that I dot and I are, so if you take the integral of I dot, you get I. So, you add the 1 by S as a gain to represent the flow from I dot to I. Now, when you have I, you need to specify the initial condition also, because you have this particular aspect we discussed when we were talking about the signal flow graph, then how to add the integrator block. So, when we integrate the I dot, we specify the initial condition. So, initial condition we consider it as I at time t is equal to 0 by S. So, that also we add. Now, next is how I is connected to E c. So, if you take this equation, I is connected to E c dot with the help of gain. So, if you write this as a E c dot equal to 1 by C I. So, E c dot is connected to I with some gain 1 by C. So, you connect this with E c dot with the gain 1 by C. So, now you have connected this. Now, finally, what you have to connect is E c dot with E c. So, again as we saw in case of I dot and I, the same we can apply here. So, we use integrator. So, E c dot, when we pass through integrator, that is 1 by S, we get the value of E c and plus the initial condition. So, the value of E c at time t is equal to 0 by S will be the initial condition which we add. So, in this way, with the help of these two equations, we can draw the signal flow graph of the electrical circuit which we just saw. Now, at the same time, you can transform this signal flow graph into block diagram. So, if you see the block diagram, you use the Laplace transform of the input. So, you get E s, then gain is 1 by L, this is the summation block. So, in this you get input from 1 by L as a gain from E c. So, E c s will be now connected to this block with 1 by L as a gain, and here you get the negative as a part of summation. So, instead of sum, it will be subtracted from the total value. Similarly, for the value of current I which you get here. So, you get R by L as a gain, and then you again subtract from this. So, when you see this particular segment, the value which you get from here is actually the value of the I dot. So, you can simply write S into I s here. Now, when you transform this through 1 by S as a block, you get the value of I s here. Now, I s here you will add the initial condition, that is I naught by S, and then you pass on through 1 by C s. So, you get the value of the E c, and plus you add the initial condition, that is E c by S. So, when you sum up both of them, you will get the value of E c s. So, in this way, using this you can transform the series RLC circuit which we discussed into a mathematical model of the circuit. So, this block diagram will represent the series RLC circuit. Now, next is to basically we have represented in the form of transfer functions. So, the alternate way can be that we represent the same into state variable methods. So, let us understand how we can represent that series RLC circuit into state variables. So, the practical approach for us would be to assign the current in the inductor, that is IT, and the voltage across the capacitor, that is ECT, as the state variables. Now, why we are choosing this? Because the state variables are directly related to energy storage element of the system, and in that L and C are considered to be the energy storage elements. Now, the inductor stores the kinetic energy and capacitor stores the potential energy, that is electrical potential energy. So, by assigning I and IT and EC at any time t as the state variable, we can have the complete description of the past history, that is the initial states of the system, and the present and future states of the RLC network. Now, the state equations for the network are written by first equating the current in C and voltage across L in terms of state variable and the applied voltage. So, using the previous equations which we just saw, in this case we can recollect and we can write in terms of the state variable. So, we can write that dEc by dt is equal to I by C. So, this you can easily get from this equation. So, you get dC by dt is equal to 1 by C I, and we do not have any forcing function in that equation. So, the components of A matrix will be 0 and 1 by C in this case. For second equation, that is the value of di by dt, we can write for EC is minus 1 by L, for I is minus R by L. So, we can compile it. So, EC against EC we write minus 1 by L, and against IT we write minus R by L. So, in this way we get the matrix A plus B matrix, you get 0 in the as a first element in B, and then next one is 1 by L, because in the second equation we have the forcing function present. So, that is anyway the input. So, you get B also as 0 1 by L. So, now the state variables in this case are basically EC and I. So, you can in simple way you can assign EC as x1 and I as x2, then you can simplify this equation as x1 dot x2 dot, that is the vector on the left, equal to the A matrix multiplied by the state vector plus B matrix into input, that is ET. So, in this way you can see that with the help of the equations which you write for the series RLC circuit using Kirchhoff voltage law can be easily transformed into state equation. Now, when you are having all those informations in hand, you can now write the transfer function of the system. Now, since we have here two variables, so we can write the transfer function in terms of EC, that is the voltage across capacitor, and I, that is current flowing through the circuit. So, with the help of signal flow graph and or maybe the block diagram which we just saw, we can compile this information. We can write EC by E, that is the transfer function for output EC. So, when you write and simplify, you get transfer function as 1 upon 1 plus RCS plus LCS square. Similarly, for the transfer function related to current as an output I by E, you can compile and you will get the value of transfer function as CS divided by 1 plus RCS plus LC S square. Now, let us take quickly the example that if you have the RC circuit in the figure, we need to find out the differential equation and then the Laplace transform of the system. So, what we can do, basically we need to find out the transfer function of the system finally. So, using Kirchhoff voltage law, you can write the input EIN is nothing but drop across resistance and the voltage across capacitance. So, ER is nothing but IR and EC you can write 1 upon C integral I dt, or if you see this figure, EC is nothing but E naught, that is output. So, you can also write E naught is nothing but equal to 1 upon C integral I dt. Now, if you differentiate the above equation with respect to time, you can simply write I by C is nothing but d E naught by dt, or you can write in short form as C E naught dot equal to I. So, now we have got one equation, then we put this into the Kirchhoff voltage law equation, that is E I n equal to R C E naught dot plus E naught. So, here what you can write in terms of Laplace, you can write E in S equal to R C S E naught S plus E naught S. So, with the help of this in Laplace domain we can get easily the transfer function. Transfer function is nothing but that is E naught S by E in S. So, you get finally that is the RCS plus 1. So, with the help of the conventional equations related to Kirchhoff voltage law or Kirchhoff current law, you can convert your circuit into the Laplace domain and then find out the transfer function of the system. Now, let us talk about the analogies. So, first we will discuss about the mechanical electrical analogies. So, the mechanical system can be studied through their electrical analogus, which may be more easily constructed than the models of the corresponding mechanical systems. So, basically we will study two electrical analogies for mechanical system. First one is force voltage analogy and second is force current analogy. So, let us first understand the force voltage analogy. If you see the mechanical system shown in the figure, we have one dashpot and one spring at which you see the mass m connected and force F is applied, which is giving the displacement x. Now, this mechanical system, the basically this is translational mechanical system. So, we have to first write the mathematical equation. So, when you write the mathematical equation, you will compare this with the mesh equation of the electrical system and then you can stabilize the analogous quantities of mechanical and the electrical system. So, let us first write the mathematical equation for the translational mechanical system, which you are seeing in the figure. So, what you can write? So, you have F equal to Fm plus Fb plus Fk. Fm is say equal to m d2x by dt2, this is because of the mass. Then Fb is b dx by dt because of the viscous friction, and then plus kx because of the presence of spring. So, you can write force F which is applied in the mechanical system equal to m d2x by dt2 plus b dx by dt plus kx. Now, let us consider a series RLC circuit where you apply voltage V and current is flowing as I. So, the electrical system which you see, we will write the equation for that in terms of voltage V. So, what you can write? You can write voltage V as R I plus L d I by dt plus 1 by C integral I dt. Let us substitute I as dq by dt in the above equation. So, what you can write now, V is equal to R dq by dt plus L d2q by dt2 plus q by c. So, this equation we have now got. So, if you rearrange, you take higher order term first. So, you can write V is equal to L d2q by dt2 plus R dq by dt plus q by c. So, now you have the mathematical equation related to electrical system and mathematical equation related to the mechanical system. Now, let us compare both of them. So, if you compare the equations related to mechanical and the electrical circuit, we will get the analogous quantities of the translational mechanical system and electrical system. So, if you compare both of the equations, you can easily find out that F, that is force in case of translational mechanical system, is analogous to voltage V in the electrical system. Mass M is analogous to inductance. Frictional coefficient, that is B, is analogous to resistance R. Spring constant K is analogous to reciprocal of capacitance, that is 1 by C. Displacement, that is x u c, will be analogous to charge q, and then if you differentiate x, that is dx by dt, you will get velocity v, and when you differentiate q, that is dq by dt, you will get current I. So, velocity v is analogous to current I. So, this example shows that how the different quantities of mechanical system are analogous to the electrical system. Let us take the rotational system also. So, where you instead of force you compare torque with the voltage. So, the analogy which you get in case of torque voltage, you first consider one rotational system where G is the inertia of the rotating body, torque T is the applied torque, B is viscous friction, and it is giving the displacement of angle theta. Now, what you can write torque T? Torque T is nothing but torque because of the inertia, then torque component which is because of the friction you have, then torque because of the presence of the spring action of the shaft. So, what you can write, total torque T is equal to J d2 theta by dt2, then plus B d theta by dt, plus for Tk you write K theta. So, now you get the equation related to rotational mechanical system. Now, you will compare this again with the series RLC circuit equation. So, what we got from series RLC circuit? We got V is nothing but equal to L d2q by dt2 plus R dq by dt plus q by c. In case of the rotational mechanical system, we got T is equal to J d2 theta by dt2 plus B d theta by dt plus K theta. Now, if you compare both of them, what you can say, that torque T is analogous to voltage V, moment of inertia, that is J, is analogous to inductance L, rotational friction coefficient, that is B, is nothing but analogous to resistance R, torsional spring constant, that is K, you can say that it is analogous to reciprocal of capacitance C. Angular displacement theta is analogous to charge q, and then again if you take the derivative of theta, you get angular velocity omega, that is equal to d theta by dt, which is analogous to dq by dt, that is nothing but the current I. So, we have seen the translational as well as rotational mechanical system, and we described the analogies with respect to the electrical system in today's discussion. We will continue our discussion tomorrow where we will discuss about the further mechanical relationship. So, in this we discussed force voltage analogy. Tomorrow we will discuss force current analogy, and then we will wind up our course. Thank you.